Have you ever thought about what it would take to create a digital master key? You know, a piece of data so cleverly designed it could trick an AI it's never even met, even one that's locked away inside a commercial black box system? It sounds like something straight out of a movie, but, well, researchers have actually figured out how to do it. Okay, let's get right into it. All right, so let's start with this image right here. It's a beautiful anemone fish. To you, to me, and to pretty much any well-trained AI, that's exactly what it is. It's an easy, straightforward, correct classification. No problem.
But what if I told you that by adding a layer of, let's call it digital noise, a pattern that is completely invisible to our eyes, we can make a state-of-the-art AI believe that this fish is, of all things, a broom. And this isn't some random glitch. Nope, it's a fundamental vulnerability in how these systems actually see the world.
So this brings up a really fascinating question, right? How can a tiny, invisible change cause such a massive error? And more importantly, could you create one of these, they're called adversarial examples, that would fool not just one specific AI, but literally any AI you aimed it at, even when you can't see or study?
This is what researchers call the transferability puzzle. See, for years, they knew they could fool the AI they had in their own lab. That wasn't new. The real trick, the huge challenge, was crafting an attack that could transfer and fool a different AI, a total black box, whose inner workings were a complete mystery.
Now, to really get this puzzle, you need to know about the two main types of attacks. First up is the non-targeted attack. The goal here is pretty simple, just cause chaos. All you want is for the AI to think this anemone fish is anything but an anemone fish. Doesn't matter what, a car, a tree, a toaster, as long as it's wrong.
Okay, the second type is way harder. It's called a targeted attack. This is all about precision. You don't just want the AI to be wrong, you want to force it to see a specific thing that you've chosen, like turning that fish into a broom. This takes a level of control that's just incredibly difficult to pull off. And here's the exact mystery that had researchers scratching their heads for so long. The non-targeted attacks, the chaos method, they transferred surprisingly well between different AIs. But the targeted attacks, the precision method, they were a total bust. An attack designed to make one AI see a broom would just completely fail on another. So the big question was, why? Why the huge difference?
To solve this, the researchers basically had to peek inside the geometric minds of these AIs. They needed to create maps of how they make decisions to figure out why one trick was working and the other one was failing so badly.
Now, what you're seeing here are visual maps of how two completely different AIs, in this case, VGG16 and GoogleNet, make decisions about an image. And at first glance, they look totally different, right? Kind of like two alien grains with completely unique wiring. Each of those colored zones represents a different classification, like cat, dog, boat, and so on.
But check out what happens when we just look at the most important part. The boundary line between a correct answer and an incorrect one. Suddenly, you see the first huge clue. These borders, these cliffs, where a decision flips from one thing to another, they're in roughly the same place for all these different models. This is exactly why non-targeted attacks transfer. A tiny push that sends an image over the cliff for one AI is super likely to send it over the same cliff for another.
But that discovery led to the second clue, which seemed to totally contradict the first. The paper found that the specific path you need to take, think of it as the most direct route to trick the AI into seeing one specific thing, like our broom, was completely different for each AI. It's like for one model, the path to broom is pointing due north. For another, it's pointing due east. They're orthogonal, basically at a 90-degree angle to each other. If you follow one path, you get absolutely nowhere with the other model.
So let's put these two clues together, because this is the solution to the puzzle. The big reason non-targeted attacks transfer is that those decision cliffs are all aligned. You just need a little nudge to fall off. But the reason targeted attacks don't transfer is because the specific, secret paths to get to a target, like broom, are pointing in wildly different directions for each AI. This was the answer.
So if every AI has a different secret path, how in the world do you find one that works on all of them? You can't, right? Well, this puzzle led researchers to an absolutely brilliant new strategy. If you can't pick one lock and have it work on another, maybe you design a master key.
What they came up with was this really elegant solution called an ensemble-based approach. So instead of attacking just one model, they put together a team of 4 different AIs. Then, and this is the clever part, they designed a single attack image meant to fool all 4 of them at the same time.
Doing this forces the attack to ignore all those weird model-specific paths, and instead find a more fundamental, more robust path that hits the vulnerabilities they all share.
And the results were just staggering. I mean, before this, the success rate for transferring a targeted attack was basically zero. It just didn't work. But by using this ensemble method, this master key approach, the success rate shot up to as high as 69%. For the very first time, researchers could reliably create an image that would fool not just one AI, but others it had never seen before.
Now, this was a massive breakthrough in the lab, but the real, ultimate test was still out there. Could this master key unlock a real-world, high-security system, one that was a complete and total black box?
Their target, Clarify.com, a commercial company with a state-of-the-art image classification system. The researchers had zero inside knowledge. They didn't know the models, the training data, the architecture, nothing. It was the ultimate test. So they generated their adversarial images using their little team of AIs, and they just submitted them to Clarify's public system to see what would happen.
The success rate was an incredible 76%. Think about that. More than 3/4 of the targeted adversarial images they made managed to fool Clarify's commercial-grade AI. The master key worked on a lock its creators had never, ever seen.
And make no mistake, this was a landmark moment. This was the very first time anyone had documented a successful targeted attack against a live black box commercial AI system. It proved without a doubt that these vulnerabilities aren't just some weird theoretical thing you find in a lab. They are very much present in the real-world systems we're all starting to rely on.
And that really leaves us with a pretty provocative final thought. This whole investigation revealed that completely different AI models, all trained independently, somehow end up learning surprisingly similar decision boundaries, which creates these shared weaknesses. So if all of these incredibly complex systems share the same fundamental blind spots, it really makes you wonder what else that's completely obvious to us are they all collectively failing to see?